Okay, so last day of class. Project is due at midnight. Final is a week from Wednesday, 8 a.m. in the morning in this classroom. Same general setup as before, so it shouldn't be any surprise. It's a 2-hour exam. My goal is to have it be less than 2 hours worth of work, but you never know how well that goes. So review. Now, okay, again, just so that everyone's clear, there will be 4 sections. Section 1 corresponds to the first exam. Section 2 corresponds to the second. Section 3 corresponds to the third. So engineering basics and material balances, vapor-liquid equilibrium and multi-component thermodynamics, charts, psychometric, all that jazz. And then the last one will be energy balances. Then the 4th section is grab bag, right? It could be combination, it could be one big question, it could be transient systems, all number of different topics. So what I'll do is I'll try and group just some general things that we talked about. Right, so the exam 1 content, if you can remember all the way back then, we had units. Right, so this could have been conversion, temperature, pressure, conversions, whatever the case. Hydrostatics. Non-reacting and reacting systems. Degrees of freedom. So these are the major general topics that we discuss, right? Hydrostatics is, rho GH in terms of what the pressure is of a fluid. Unit conversions can include a lot of different topics. For non-reacting and reacting system balances, we have a number of different ways to accomplish them. So we have atom, molecule, and extent of reaction. The most difficult part with the reacting and non-reacting balances is almost always going to be the design specifications. These strategies here are relatively straightforward, but the tricky part is converting a design specification that is written down in the problem statement to an equation that's a function of the masses or the molar flow rates. That's the tricky part of the reacting and non-reacting system balances. But these are the general topics. Now there's some other things in there like wet basis versus dry basis, if you remember that. And for all the sort of small here's and there's, you have the study guide. Exam 2 was all thermo and phase behavior. Just everything that's thermodynamics that is not explicitly an energy balance is basically what we covered in exam 2's content. Well, actually, the first thing we talked about here was equations of state. So this includes the ideal gas law, the virial equation, cubic equations of state, compressibility factor, a number of different ways that we can calculate or basically relate between temperature, pressure, and specific volume. The one we're generally the most interested in is the specific volume, because that allows us to provide you with a design specification in terms of volumetric flow rate, and then you can convert it into some sort of a molar flow rate. That's going to be the one that we're traditionally the most interested in. Then we talked about multi-phase systems, vapor pressure, and from here we started talking about humidity, and vapor liquid equilibrium, which includes Raoult's law. This is for multi-component / one condensable component. So in this case, the one condensable component, this is where we're talking about humidity, saturation, relative humidity, relative saturation, all of those different definitions. Within the multi-component category, we have TXY, PXY, and flash calculation. And let's specify more specifically dew and bubble points. Here's a key concept. What is the difference between the dew and the bubble point and the flash calculation? What is the difference?
The dew and bubble point are just specific conditions.
Can you expand on that? What specific conditions define the dew and the bubble point versus the flash?
The dew point is when the x sub I equals z sub I, and
So could you phrase that more generally to apply to both the dew and the bubble point? Yeah.
So is it that the flash calculation gives you more fractions, and the dew and bubble pointers just give you certain points on temperature or pressure?
Almost. The flash calculation, so the dew and the bubble point give us the mole fractions. And these are the same mole fractions in the flash. But there's one thing that's different. It's not the mole fractions, it's the...
Doesn't the flash have a system conditions, whereas dew and bubble kind of like basic terms?
So dew and bubble, they happen in specific temperature and pressure conditions as well. Temperature, pressure, composition, same thing with flash. But it's not the composition of the phases. What's the other key piece of information we need to know about the phases? How much of each of the two phases we have. So in the flash calculation, it could be any quantity. It could be 100% vapor all the way to 100% liquid and every point in between. In the dew and the bubble calculations, you have an infinitesimally small amount of one of the two phases that forms, which allows us to do the, z is equal to y or z is equal to x. But the key thing to remember is that all of these calculations use the same set of equations. The difference between doing a TXY, a PXY, a flash, or a dew or a bubble calculation is in the assumptions that you make. So all of the equations can all be used to solve all the problems. So for example, the bubble pressure equation we can use this equation to solve for the flash calculation, because this is all we've done here is substituted, Raoult's law into the summation of yi. So in this case here, we took yip equals xi star and plus the summation of yi equals 1. That is how we derive this equation. But to derive this equation, we've made no assumptions mathematically. But then to take this equation and decide, am I going to do a dew or bubble point calculation versus a flash calculation, that's where I start to insert my assumptions. Does this ring a bell? This is a very important concept because you will get a lot of vapor-liquid equilibrium questions. The more quickly you can solve the vapor-liquid equilibrium questions, the easier time is going to be on the rest of the exam. So this bubble pressure equation, the dew pressure equation, Raoult's law, you can use any of them as a starting point. Right? So if you know the liquid composition but you don't know the gas one, boom, plug this in. If you know the gas composition but you don't know the liquid, use this one. E equals 1 over summation of yi over. So you don't have to rederive these equations. You just know how to use them and apply them. But here, this is the key part, just differentiating between a dew and a bubble pressure calculation and a flash calculation. That is the critical part of all this, is the assumptions that go into it are what differentiate everything. So within here, we also talked about triangle diagram, psychometric. Let's see, did we do any other diagrams? So it's psychometric, compressibility, TXY, PXY. I mean, I guess general phase diagrams. I'm trying to think, is there any other ones that we didn't use? That we used? So, in this section here, a lot of it is probably going to be diagrams in general vapor-liquid equilibrium questions. You should expect some sort of a flash calculation. Right, so remember, the flash calculation, it's not just the composition, it's the total quantity of phase. So we typically refer to a flash calculation for vapor-liquid equilibrium, but in general, this is a more general thermodynamic concept. What is the composition of every phase and how much of every phase? That is a flash calculation. Exam 3, which is fresh in our minds. This is energy balances, reference states, delta H for temperature changes, pressure changes, phase changes, and delta H of reaction, which is directly related to the heats of formation. Not obviously in this functional form. Right? The delta H of reaction is the summation of the stoichiometric coefficients. So I got a lot of somewhat concerning questions while working on the project related to these topics, rather all of these topics here. Reference states, temperature changes, pressure changes, phase changes. And we talked about that on Friday. Let's just do a quick question. How do I calculate the enthalpy associated with a pressure change of a gas?
You ignore it.
We don't. Right? We're assuming ideal gas behavior for most all of our calculations. Thermo 2 will tell you how to calculate pressure changes based on gases. It's not a straightforward process. It's a fairly involved, more or less, solving a partial differential equation. But you can solve it creatively. Temperature changes. How do I calculate internal energy change with an ideal gas? Internal energy. Delta U from T1 to T2 for an ideal gas is equal to what? It's not CP. CV. But what about it? Do I assume it's constant or not? So I can get C sub P from the back of the book. I just need to subtract R from it, and that gives me my C sub V, constant volume heat capacity. Phase change. How do I calculate this? Do I calculate it?
No.
We look it up. So typically, if I'm looking at vapor-liquid transition, that's the heat of vaporization. That is only tabulated at one temperature. We have to make sure that we can calculate the heat of vaporization as a function of temperature. Similarly, can you calculate the heat of reaction as a function of temperature? On exam 3, we had the heat of reaction as a function of the phase. Right, that was question 2 on the exam. You were given the heats of formation of the liquid, and I asked what is the heat of reaction in the vapor phase. So what you had to include was the heat of vaporization. Right, so the heat of reaction as a function of temperature is the enthalpy of the products as a function of temperature minus the enthalpy of the reactants. Well, this could be a function of temperature, pressure, phase, whatever the case is. Right? That's the delta H of reaction. Delta H of vaporization is the enthalpy of the vapor phase minus the enthalpy of the liquid phase as a function of temperature. Right? Delta is always final minus initial. So the definition for vaporization is gas phase minus liquid phase. We're going from the liquid to the vapor. That's just a definition. Right? We could have defined it all based on condensation. Yes?
Sorry, going back, your expression for CP, is that supposed to be CP plus R? Is that supposed to be-
Yes. Got ahead of myself. For reactions, we're defining the heat of reaction as the products minus the reactants. Final state minus initial state. Again, just a definition, it's a convention that we've used. But it makes sense because we're starting off with reactants, we're forming products. But all of these involve going from a reference state to whatever the final conditions are. I can't tell you how to get there. So on the project, there are a number of different ways to go from the reference state, which is what you guys get to define on the project, to the final state, which is defined based on the process specifications. Do you want to heat it first, then vaporize it? Do you want to vaporize it, then heat it? Do you want to pressurize it, then heat it, then vaporize it? All of those are valid options. You might get slightly different numbers because we are making some assumptions in our calculations, namely ideal gas phase behavior, and sometimes you might not have the most accurate data available. Right? I'm kind of disappointed in the Felder book. It has, I think, just a constant heat capacity for water, liquid water, which is, I wish they would have been a little bit better than that. Right? So based on the data that you have, the pathway you choose is going to introduce some uncertainty because you don't have 100% completely perfectly accurate data. So that's why these are going to change a little bit. Now the only thing in addition to this here, and I'm not going to spend too much time more on this, is the transient systems, which were the focus of a good chunk of last week's homework assignment, and we talked about it for a few days in class. So those are going to be valid. Now I'm not going to expect you to solve a boatload of differential equations, but I do expect you to be able to derive expressions for the rates of change. Right? So if I said, oh, you're filling a swimming pool and you're filling it up with this much and then it's draining at this rate, write out the ordinary differential equation. That's something that I will definitely type of thing ask. Or, it snows X number of feet in the mountains in February and it melts this much based on this condition. What is the equation for the height of the snow at Snowbird Ski Resort as a function of the day? Right? So you're going to have to derive the differential equation. Now, one of the main things that we talked about when we were doing the transient systems is that everything started with a material balance. Right? But then we inserted in different expressions to relate this to like the height or the volume or some other parameter. Right? Using the density or something like that. So on the questions on the homework, you were filling a gas tank with another gas tank. In that case, you started off with a material balance, but then you substituted expressions in to solve for the pressure as a function of time. So being comfortable substituting an equation of state or a density expression into the material balance, that is the basis for doing the transient systems to make them really useful for a number of different equations. Do anyone have any questions on that? I think everyone hopefully you didn't neglect it completely because it will be on the final exam. Yeah.
I have one question about the equations of state.
Mm-hmm.
On that exam 2 we were given, you said we would be given the virial and the cubic.
Yeah, I'm not going to expect you to write that down.
Okay.
So if I give you a complex equation of state, I'll give you the equation of state
Okay.
and the necessary parameters. Yeah. So just be familiar with how to apply them, what the units of the different coefficients should be. Right? Those are all types of questions that you might be asked. But you'll have the equation there. And you'll say A is this, B is this. All right. Any other questions? So let's quickly go through our example problems. We might not have a chance to go through all of them, but at least we can set them up. So let's take a look. Let's first dissect these questions and see if we can identify what are the primary concepts that I'm trying to test. And this might be a useful exercise on the exam to know what's a good starting point. Okay? So, question 1. Let's take a look at it. So compounds A and B enter a distillation column in equimolar ratios. We have design specifications. 80% of A is recovered in the top stream, and the ratio of A to B is 3:1 in the bottom stream. What am I trying to test here? What topic on the board is this?
Just molecule balance? Or yeah.
This is a non-reacting material balance with design specifications. So this one will go on section 1 of the exam. Next question. The volume of air is trapped in an inverted container at the bottom of a swimming pool that is 5 meters deep. The pool is at 20 degrees Celsius. What is the specific volume of the air? What am I asking there? Right, anytime you hear volume, you either think density or equation of state. Right, so this question, first part, asks for an equation of state question. Second part, what is the volume fraction of water in the air? Raoult's law. Now, this one's a little bit tricky because I said volume fraction, but volume fraction is the same as mole fraction for ideal gases. Next one, obviously, is an energy balance, reacting system energy balance. But on all of the exam questions, will all be written to test on one of the concepts or a combination of the concepts. And so far, you've had 3 different exams and 3 different practice exams. So that's like, 40 questions worth of material. And you'll notice that on most all of the questions I ask, if I break it down into parts A, B, C, and D, for example, they each tend to test a slightly different concept. Some of the problems, if there's just one big point, right, I'll have multiple concepts tested within the problem. But if it's broken down, just think, okay, what is question A asking? Oh, this is a Raoult's law question with one condensable component. I know what equation to use. Oh, this part is a non-reacting material balance. Or let's say, for example, on question 3, this handout here, perform a material balance and construct an enthalpy table. Right? Part A is a reacting system balance. Part B is construct an enthalpy table, choosing a reference state, and calculating. So every single part can be distilled to one of the concepts on the board. Don't think that you can just figure it out by moving numbers around. We have talked about specific strategies to handle every single one of these conditions. The difficulty in this class is not in the mathematics. The math in this class is vastly simpler than what you've already accomplished. Right? So most everyone here has had their ODEs in line algebra, right? Almost everyone's had numerical methods. And a good chunk of you, if not most of you, are in either PDEs or quantum. We are so much more simple in math than all of those classes are. Now, I don't know where you guys think this class fits in the relative difficulty of things, but I think that the difficulty of this class comes in the synthesis of ideas. We're taking a collection of maybe 30 to 40 relatively simple individual concepts, but we are adding them together in effectively an infinite number of ways. So the difficulty in this class comes from translating the written description of a chemical process into a mathematical form where you can substitute in different equations. Ideal gas law, virial equation of state, Raoult's law, species balance, total balance, calculating delta H's, converting a design specification to flow rates. Once you get the equation, I trust that everyone here can trivially solve the equations. The hard part is grabbing all of the different concepts together and putting them into one. Oh, we forgot. Question 2. There's one more concept in this question that we didn't talk about yet. Hydrostatics. So question 2 combines hydrostatics, equations of state, and Raoult's law into one equation. So individually, I trust that if I said, what is the pressure at the bottom of a pool 5 meters deep, everyone would nail it. But as soon as I insert it into a different question, then it starts to be really confusing. Well, how am I supposed to know what the density of air is? I don't have a table to look it up. Oh, equation of state. So take every question that you see on the exam and break it down and distill it to one of these core individual concepts. And it'll make the process go a lot smoother. Because that's how I write the exams as well. I look at basically all the things on the board, all the things on the study guide, and I think, which ones do we spend the most time on? Which ones do I think are the most important? And I try and add them into the exam in those ratios. If I put all the concepts into one question, it makes it brutally difficult to grade. So I try and break it down to have individual questions testing only 1 or 2 concepts. But on the final exam, I'm going to expand that scope a little bit because it's a comprehensive final. So a lot more concepts are going to be lumped into individual problems. I'm going to put a particular problem that I think has a focus in one area versus another, right, in section 1, section 2, or section 3. But don't think that all the questions in this section are going to be completely independent of maybe Raoult's law. And all the ones in this question are going to be completely independent of material balances. And all the ones in this section here are not going to use material balances either. Right? They are going to use all the individual concepts. But the difficult part should be related to 1, 2, 3 exam content. Hopefully that strategy helps. But go back through the exams, resolve the problems you may have missed, and think to yourself, what are the key concepts that are being asked here? And deconstruct the problem and look about it in sort of a sequential process. Yes?
On number 2, the container at the bottom, we have to assume that was like a compressible container, right? Like it couldn't be like a glass jar.
No, so I said a volume of air is trapped in an inverted container. I'm thinking like a glass that flipped upside down and you just push it to the bottom.
Will the air compress as you go down?
Mm-hmm.
Inside the
Same thing. You could also think of this as like a balloon. You fill a balloon, you pull it down, the water pressure will squeeze the balloon. But in this case here, water has to be able to evaporate into the air. So there has to be a liquid-air interface. So I'm thinking like take a Tupperware container or a bin and then just pushing it down to the bottom of the tub. And that air is going to compress, and then the water and air are going to be in vapor-liquid equilibrium at the bottom. And so on these ones, these are kind of slapped together. So they're not as rigorously explained as they would be on an exam. Like so, question 2, right? You don't have the vapor pressure of water at 20 degrees C and that kind of stuff. So there's some information that's missing, but it's all pretty well-known parameters. Same thing with like the density of water for the hydrostatics. Okay, let's just go through the number quickly and set these up. So we have a 50-50 mixture of A and B going into a distillation column. So we get to choose a basis. Well, see again, like I said, these are pretty slapped together questions. So I'm asking for the flow rates of A and B in the top and bottom stream, but I don't give you the flow rates in and out. So that's a bit of a disconnect. So let's just say, let's assume a basis of 10 moles per second coming in, which means it's 5A and 5B entering into the system. So let's do a degrees of freedom analysis. We have, call this 1. Let's see, what did I call these in solutions? 2 is the top stream, is what I call it. This is 2, this is 3. So we don't know NA3, NB3, NA2, or NB2. That gives us 4 unknowns, minus 2 material balances. Right, we get 1 material balance per independent species. That could be an A balance and a total balance, it could be a B balance and a total balance, or it could be an A balance and a B balance. We get to decide which ones we choose. So we're going to need 2 design specs, which we do have, to give us 0 degrees of freedom. So we can't solve this problem. And again, this is how I write these questions. How much information do I need to give you so that it can be solved? So the first design specification, 80% of A is recovered in the top stream. Now here's the hard part. How do I translate this into an equation that I can substitute into my A balance and B balance? In fact, let's jump the gun and let's write out the A balance and B balance. Now, in an exam scenario, and by the end of this class, it should be automatic. There should be zero hesitation whatsoever in writing out material balances. You should be able to hammer out 6 material balances in 20 seconds. Because then, it's just in and out. Don't hesitate. Don't think there's got to be a way to simplify this. There might be a trick that I can use to make this easier. Don't. Write out the material balance instantaneously. 5 is equal to Na2 plus Na3. The B balance. 5 is equal to NB2 plus NB3. Done. And the time it takes you to think about, is there a different way to solve the problem, you could have written out the material balances. So just do material balances, just do energy balances, just write down Raoult's law, just write down the starting point for all the calculations, and you will get points on the final exam. If you distill the questions down to these core concepts, find the equation that is the starting point for every single one of those concepts and write it down. Don't hesitate, write it down. Okay, how do I translate my first design specification? 80% of A goes to the top stream. Mathematically, how do I write that down?
So 5.
5 times 0.8 equals 8.
So Na2 is equal to 0.8 times 5. I'll just write it as Na1. So if I want to get an equation with 0 degrees of freedom, this one has 2 degrees of freedom. This one has 1 degree of freedom. I can solve for this, substitute it here, solve for this. And from there, we can get that Na3 is equal to 1, Na2 is equal to 4. Next one, design specification. The ratio of A to B in the bottom stream is 1 to 3. How do I write that as an equation? So let's see, N, we're relating Na3 to NB3. So which number should I put here and which number should I put there?
3.
So we have more B in that stream, right? So this would be like that, right? It's always opposite of what you think when it's a ratio. So the other way you could write this too is that 1/3 is equal to, let's see, 1/3 is Na3 over NB3. And then when we cross multiply, we get this equation here. Now again, substitute this into this, and we'll get our answer of NB2 is equal to 2, NB3 is equal to 3. Simple, basic algebra, something that is no more difficult than would have been encountered in an 8th or 9th grade class. The difficulty is in deriving the equations based on the problem statement. But we've been talking about this problem for a while. This problem would only take a minute or two to solve. Right? If you see the problem, you identify this is a non-reacting system material balance. I understand the degrees of freedom. Here's my material balances. I need to substitute in some unknown equations with design specifications, right? Because this part here, this part took you no time, right? That's free time. Right? And the time it takes you to scratch your nose, these two equations are already on your paper. Right? So all your time has to be spent deriving these two equations and then just doing a little bit of algebraic substitution. This is no more difficult than a question that would be worth somewhere between 5 and 10 points on a final exam. And it should only take a few minutes because you guys are really quick at your material balances. Okay, question 2. We have a combination of concepts here. What is the specific volume of the air? What is the equation that I'm not going to think about, I'm just going to write down? air volume that says
Ideal gas law.
equation of state, PV equals nRT. You know what? That doesn't give me specific volume. PV hat equals RT. I solve for that. I need pressure. What's the next concept? Hydrostatic hedge. P is equal to P0 plus rho GH. Again, this is an equation you already have on your sheet, right? And it's an equation we've used a bunch of times. Write it down on the paper. You're going to get some points. P0, 101,300 pascals. The density, 1,000 kilograms per cubic meter. 9.8 meters per second squared. H, 5 meters. Okay, we put this all together. Our pressure is 150,300 pascals. If we use SI units, it all works out. Right? These three things times together gives us a Pascal. Then if we substitute everything together into our equation, 8.314 meters cubed pascals per mole Kelvin. Temperature is 20 plus 273 Kelvin divided by our pressure, 150,300 pascals. Crunch the number in our calculator, 0.0162 meters cubed per mole. Last part. This is worded a little bit weirdly. I'll give you that one. What is the volume fraction of water in the air? Let's solve the problem as if. I guess we didn't really talk too much about volume fraction, but volume fraction is the volume of I divided by the total volume. Substituting the ideal gas law, nRT over P, nRT over P. R's cancel, T's cancel, P's cancel, N of I over N is the mole fraction. This is water in air. That is our Raoult's law with one condensable component. The mole fraction of water is equal to the vapor pressure of water divided by the total system pressure. We have the system pressure. One thing that you are not given is the vapor pressure of water, 17.5 millimeters of mercury. For every 760 millimeters of mercury, we get 1 atmosphere, which is 101,300 pascals, divided by 150,000 pascals. And the mole fraction of water is 0.0156, so about 1.6% water in the system. Questions? All right, the last one we're not going to have a chance to go through completely. But I want to spend a few moments dissecting this problem, and I'll give you the final answer so you guys can work through it on your own. So, question 3. It says it's a vapor phase reaction occurring at 600 degrees C, where 2A forms 2B. The conversion of A is 25%, and pure A is fed to the reactor at 150 degrees C. So, let's look at our data sheet. Because the hardest part of all of these problems is constructing the enthalpy table based on a reference state. We have to add in all the different contributions from temperature changes, from pressure changes, from phase changes. Which ones are we going to have to include? The reactor occurs so A is fed to the system at 150 degrees C. So based on our data table, what phase of matter is A in when it's being fed? Liquid. What is the phase of matter of A when it comes out of the reaction? So let's just talk really briefly about how do we calculate the H for A going into the system. What are the steps based on the data that we have available? So we'll take a volunteer just so it's crystal clear. What is the equation for A? Yes. Is that a volunteer answer?
So I would heat it up to 200.
No, we need one step before that.
You figure out how many moles. Oh, find the. What?
So I need an H value for a reacting system
Delta H.
for A. Delta H formation is number one. Then the next step is
And heat to 200
with,
liquid heat capacity.
okay,
Then vaporize.
okay,
Then heat to 600 with liquid.
yep, so that'd be the outlet conditions. So for the inlet conditions would be what? So that's a 600 degrees C. We create the liquid, we heat the liquid to its boiling point, we boil it, we heat the vapor to the final 600 degrees C. What about the inlet conditions? The inlet is 150 degrees C of component A. That's in the liquid phase. So what is my equation for H in that system? Yeah.
So you use the standard heat of formation and then you heat it to 150 degrees C from the reference temperature, which is 25.
Yes, bingo. So H of A in is going to be equal to the delta H of formation at the standard state, which is 25 degrees C, plus 25 to 150 C sub P of liquid A dt. In this case, it's a constant heat capacity, so this would just be C sub P liquid A 150 minus 25. This is a common mistake that I always see. Making sure you get the order right. Initial, final. Final minus initial is our delta. That's our delta T, is final minus initial always. So H of A out, delta H formation of the liquid, let's put the liquid here, plus integral of 25 to 200 C sub P of liquid A dt, plus the heat of vaporization of A, plus integral from 200 to 600 C sub P of the vapor of A. That's the formula. Now for B, let's talk about B. What is the process for B? What is my equation for H hat B out? Because it's the only one we have to bother calculating, because there is no B fed to the process. What is my formula? Volunteer. Yes.
Since the X of the boiling point is 250.
So this which phase is it in for B?
It's in the vapor, so it leaves
Okay,
it.
so what is my series of delta H's that I'm adding together to calculate my enthalpy value?
Formation liquid.
Heat of formation of the, what data do we have on our table?
Oh, vapor.
Heat of formation of the vapor phase. Then what else?
We need to go from 25 to
Yeah, can you go all the way to 25 to 600?
We can. That's the data we have available. That's the path we've chosen. So, 1, 2, 3 enthalpy values. That's all that's necessary. The only thing that we need to do now is the material balance. How do I want to do the material balance? Yeah, question.
Sorry, I just had a question about that one.
Mhm.
So I understand that we can use the delta H formation in the vapor, so that's including the heat of vaporization in that term, right?
Yes.
But when we're going from 25 to 600, we're just assuming that it's one heat capacity, because in the table we're getting, there's a difference between the liquid and the vapor heat capacity.
There is, but we don't need to use the liquid heat capacity because we can already directly form the vapor.
Okay.
Same thing like in the project, if you choose your heat of formation correctly, you can kind of lump in your heat of vaporizations within it. And so that's why we're just, so this here, right, this term, the heat of formation of the vapor for this particular species, right, normally it would not want to be a gas at 25 degrees C. So you're creating the liquid, then you're vaporizing it immediately, add those two together, and that gives you the heat of formation of the vapor phase species. So someone pre-calculated that, me, in this problem. This is just made up numbers anyway. So let's talk about the material balance really quickly. Which ones can we use and which ones can't we use?
Can you use extent of reaction?
We can use extent of reaction, we can use molecule balance, but why can't we use an atom balance? Exactly. We don't know what's going on in this one here. My default is almost always to go with the extent of reaction, but this one here could pretty readily be solved as well from a molecule balance. So the conversion, in this case here, is equal to 25% or 0.25. Now remember, the conversion is a definition, and I can never remember the equation, so I always have to rederive it. It's n out minus n in over n in. Let me double check that I get this right. If nothing reacts, then the out is equal to the in, because nothing changes. That gives me a conversion of 0. That makes sense. If everything reacts, that means I have nothing coming out. Hold on a second. In minus out over in. If everything reacts, then there's nothing coming out, and a conversion is 100%, so this is backwards. It should be n in minus n out. Right? So that if nothing comes out, that means n in over n in gives me 1, and that's 100% conversion. So now I just need to translate this to an extent of reaction approach. So n of A is how much comes out, is equal to n out n in minus the extent of reaction. And between these two formulas, we can solve for the extent of reaction. NB would be equal to 0 plus 2 extent of reaction, and then we can solve our problem that way. So the number that I got in this process here is that Q is equal to 65.63 kilojoules into the process.
What was the molar basis?
This is 1 mole of A going into the system. So that's another example problem that we can use. Okay. Questions? Last minute questions.
What are the answers for the problem?
I will let you know when I write it. Thank you guys very much for your hard work and attention. Please do go online and fill out the course evaluations. Generally speaking, we only get evaluations from sort of dedicated students and really vengeful students. And the middle of the class is kind of bottomed out. So if the middle of the class and everyone else could just fill out the evaluations, we don't get these, oh, he's great versus, oh, he's terrible. That's typically what we see in course evaluations. So please do take the time to fill out the course evaluations. They do matter and they do make a difference. But, I will be out of the office most of this week. I will be back next week. So no office hours, but please email me with any questions you have, and I will try and respond accordingly. Have a great summer, and see you at the final.